So good morning for those that already entered. I believe that we can start just with a brief introduction, and the rest will arrive soon. Okay, so good morning, everyone. I'm Raquel Santos. I came from CITEV, and today we are starting the training activities from Ways to be a Comp, and this is a series of workshops and webinars from CITEV, which is one of the partners. And today we are starting the training, which aims to develop training materials for a skilled workforce for biomaterial-based manufacturing activities in the textile, footwear, and packaging value chains. So if you go to our website, you will see the different training sessions if you have more interests in other teams as well. So please go to our website in the training section to see other training materials or training activities that might interest you. Today, I will just briefly introduce CITEV. CITEV is the Textile Technological Center from Portugal. We are located in Vila Nova de Famalicão, and we provide numerous services in the textile and clothing sector, mainly testing, product and process certification, research, technology development, and engineer. Also, some services around sustainability, circular economy, bioeconomy. Also, we have the departments for manufacturing and digitalization, Industry 4.0. We also have CITEV's Academia, which is about training, coaching, and we support also our companies in innovation and entrepreneurship. And we have also this international consultancy in design and fashion intelligence. So we are market oriented for mainly fashion and textiles, but we also have sports, defense, mobility and transport, workwear, health, architecture and construction. So basically everything that is around textiles. So today we are gonna present the first workshop of this series, which is life cycle assessment. And today we have Luís Ramos, which is my colleague from CITEV, and I will pass the virtual stage to him. So thank you, Luís, and I hope everyone has a a good workshop. I'll be here around if you need. So please let me know if you need cameras or microphones. Okay? Thank you.
Okay, thank you, Raquel. First of all, I'm going to share my presentation. Can you see? Yes? Okay, I believe so. So first of all, I would like to thank Raquel for the invitation to give this workshop about life cycle assessment, which is a matter of with such importance nowadays, where we want to assess the sustainability of our products, of our services, and even on the projects that we are working. So, in life cycle assessment is the basis methodology to assess the environmental impacts of products and elsewhere. So first of all, I would like also to and also of course to thank all the participants in this webinar to join us today. And I also want to introduce myself first, of course. My name is Luís Ramos. I have an academic background in chemical engineering, and I work here in CITEV for already 10 years. First as an energy specialist, but in the more recent years, since 2018 or something, I work also in the environmental consultancy and also sustainability consultancy and the application of sustainability methodologies such as life cycle assessment and also carbon footprint studies. I work in a team with more people in the Department of Technology and Engineering of CITEV, and we have lots of activities in the field of energy and environment and sustainability, such as performing energy audits and energy rationalization plans, some energy consultancy, wastewater characterizations. Also in the field of sustainability, like I said before, we perform also LCA studies, carbon footprint studies, and this kind of studies. And we also participate, of course, in projects like this and other national projects. And we also give training to companies about in these subjects. So this session is about life cycle assessment. Of course, life cycle assessment is a very broad methodology which is applicable to a very broad of more or less to all sectors, to all sectors of activity. But as we are a technological center, this presentation is a little bit more focused on textile and on textile products. The examples that we are talking about are from textile, and also the focus is more the textile. But of course, this methodology is applicable to other sectors as well. The meaning of this presentation of this webinar is to make you familiar with life cycle assessment methodology, and also to life cycle assessment terminology, which there are some very specific terms that maybe we have already heard about, like impact categories, environmental impact categories, or allocation, or life cycle inventory, and we will speak about it during this webinar. So the webinar will be divided in these main topics. First, and of course, before to go to life cycle assessment methodology, we will speak a little bit about the life cycle of a textile product, because we believe it's important. I believe it's important to know what is the definition of life cycle, and also what is the typical life cycle of a textile product, and the environmental aspects associated to the life cycle of a textile product. Then we enter in the life cycle as it is, in the life cycle assessment as it is. We will speak about a little bit about the concept of life cycle assessment and the main applications, and also the main advantages and weaknesses of the life cycle assessment methodology. Then we will enter in the methodology itself. Of course, we will analyze what is said in the main standards that regulate life cycle assessment, which are the 14040 and 14044, with the main phases of life cycle assessment: goal and scope definition, life cycle inventory, and the impact assessment and the interpretation. And if we have time, and I believe we will speak a little bit about two methodologies that are very good to communicate the life cycle assessment results and to communicate the environmental impacts of our products, which are the environmental product declarations, or EPDs, and also the product environmental footprint, or PEF, which is a proposal of harmonized methodology to communicate and to study environmental impacts of products proposed by the European Union. And then I will keep the last 15 minutes, more or less, for questions. And also, as also an introduction, between life cycle inventory and life cycle impact assessment, we will make a 10-minute break to give some time for you and for me to rest a little bit, and then we start after 10 minutes for the rest of the webinar. Of course, as this is usually in this kind of training sessions, when they are presential, I ask also to the participants to give a brief introduction about themselves and also about their perspectives on the training session. But as it is an online webinar, this is very difficult, and also the list of participants is very extensive, so it's difficult. So I will not do it today. So let's start. But anyway, feel free to make any question. If you have some doubts, feel free to interrupt and to make questions. Don't if you don't want to keep all the questions to the end, feel free to interrupt and make the questions and put your doubts on the table. And I will try to clarify those questions and those doubts. So before to go to the methodology of the LCA methodology itself, let's speak a little bit about what is the life cycle, and especially what's the life cycle of a textile product. So the definition of life cycle according to ISO 14040 is that it's a consecutive and interconnected stages from obtaining raw materials or their production from natural resources to their final destination, until their final destination. So it usually, for any products, it usually to start with the raw material extraction and production, then the manufacturing, the process, the production process, or the manufacturing process of the product itself. And then we have the use of that product, and at the end, the end of life of that product. And in a linear perspective, it is as it is presented in the figure that you can see. We start raw material extraction, manufacturing process, use, and then the end of life, which generally is the disposal or the incineration or the incineration of the product. So going especially to the life cycle of a textile product, it starts with the production of the fibers, and the fibers can be natural natural fibers such as vegetal natural fibers like cotton and flax, or animal natural fibers like wool. But it can also be synthetic fibers as polyester and polyamide, or artificial fibers like viscose or lyocell. So we have a very broad, very broad raw materials, fibers to provide the textile sector. Then, after the obtaining of the fibers, we have the production of the yarn, usually in a spinning mill. We produce the yarn, then we pass through the production of the fabric, and the fabric, it can be a woven fabric or a knitted fabric or knits. And if it is a woven fabric, we have a weaving mill. If it is a knit, we have a knitting mill. After that, we have the wet treatment, which can include the pre-treatment, like mercerizing or singeing or desizing, and we have also the dyeing of the product and the finishing activities. After that, we have the garment baking, and then we have the retail and distribution, and after that, the use of the textile product and the end of life of the textile product, that nowadays is more a disposal or sometimes the incineration, but we want that we want that the recycling rate of the textile products to increase, and we want to close that loop the maximum that we can. So starting for the fiber production, I think it's important to retain that information. When we speak about fiber production, we may have in mind that most of the fiber production in the world, the global fiber production, is associated to synthetic fibers, namely especially polyester, and also some plant fibers, especially cotton. If we sum the production of polyester and the production of cotton, it represents more or less 87% of the total fiber production. These are numbers of 2023, numbers presented by Textile Exchange. So when we are speaking about the production of fibers for the textile industry, we need to have in mind we are talking about especially about polyester and cotton. And we can see also in the graph on the left, in the figure of the left, that the consumption of textile, the global production of fibers for the textile industry is increasing, and the trend is to continue to increase. And also the production of polyester and cotton, especially polyester, it's estimated to increase significantly until 2030, as we can see in the figure. Another thing that is very important also to have in mind, and of course for this project, which has which means to reuse some ways to produce new products, is that for nowadays um, the production of recycled fibers only represent about 7% of the total fiber production, and most of it results from the recycling of polyester bottles that are used to produce polyester for clothes. So when we are speaking about the recycling of the textiles itself, it represents around 1% of the total fiber production from 2023, as we can see in the figure presented there. And most of the recycled fibers are from polyester, as we also can see there. And of course, another important information is that we are speaking about 124 million tons of fibers which were produced in 2023. So, and taking that into account, we are speaking a little bit next about the environmental aspects of the production of synthetic fibers, namely polyester, and also the environmental aspects associated to the production of cotton fibers, which, as we could see, are the two main fibers that are used in the textile industry. So the main environmental aspects associated to the synthetic fiber production are, of course, the huge energy consumption, electric energy, but also thermal energy consumption, fossil fuel consumption, not only to produce energy, but also the raw materials for the synthetic fiber production are also fossil fuels. The consumption of chemical products, and this are the consumptions. When we are speaking about emissions, of course, we have emissions of pollutants to water, emission of pollutants to air, and emission of pollutants to soil with the waste generated by these activities. When we speak about the main environmental aspects of natural vegetal fibers, the production of natural vegetal fibers, we are mostly speaking about the water consumption, which I believe some of you knows that the water consumption of the cotton production is huge, is very huge. And also the use of the consumption of fertilizers and pesticides. There are also some varieties of cotton, like the organic cotton, and also types of cotton that are using each time less pesticides and less fertilizers. But the conventional cotton, which is still the most used, use a lot of fertilizers and pesticides. And we have also the land occupation, as we can see in the figure. The size of the cotton cultivation plants are also very big. It occupies a lot of land. When we speak about emissions, we are mostly speaking about emissions of pollutants to water and to soil, mainly due to the use of fertilizers and of fertilizers and the nitrates and the phosphates. The phosphates of the fertilizers are going to water, and are going also to the soil where the cotton is cultivated. And we have also, of course, some toxic substances derived from the pesticide use also. Then we can speak a little bit about the main environmental aspects of the conventional textile production process, as we saw in the figure before. And when we are speaking about spinning, and we have in that figure the conventional or the traditional process of a spinning mill, which starts with the opening of the cotton, and then the carding process, the drawing, the weaving, the spinning itself, and after that the winding, and sometimes, not all the times, but sometimes also the steaming or humidification of the yarn. As we can see in the figure, the main inputs in the spinning, the main environmental inputs in the spinning mill is the electricity consumption. Spinning mills consumes a lot of electricity. They only consume thermal energy if the mill has the process of steaming or humidification, and of course in that case it's not there, but they also consume some quantity of water. When we are speaking about outputs, the main outputs are of course the waste, the generated waste. And when the spinning mill has the steaming process or the humidification process, it usually has a boiler to produce that steam, and there are also some air emissions associated to the spinning mill. But keep in mind that spinning mills, the most important environmental aspects regarding the inputs is the electricity consumption. Regarding the outputs, it's the generated waste. Then, after the yarn is produced, we will produce the fabric, the woven fabric or the knits, and for the production of woven fabric in the weaving mill, we have the main the most used process starts with a preparation for weaving, which is composed by warping, by the warping process and the sizing process. When the companies have sizing, of course, those mills have more environmental impacts than the mills that don't have that process, because that process uses I'm sorry, that process uses thermal energy. Beside electricity, it uses thermal energy in the form of steam generally, and they use also chemicals, at least the sizing agent. And of course, using thermal energy, it has air emissions, and it has wastewater and also waste. The weaving process itself consumes electricity and generates some waste also, as the inspection process. When we are speaking about knitting, we have the preparation for knitting, the knitting process itself, and the inspection, and most of it, the most important environmental aspects are in the inputs is the electricity consumption, and the outputs, the waste generated. So then we go for the phase of the textile production process which has most associated environmental impacts, which is the finishing process, which can be divided in a finishing or wet treatment. Which can be divided in the four main stages. Pre-treatment, and this pre-treatment can be composed by singeing process, resizing process. When we have sizing of the yarn, of course, we have to remove the sizing agent, and we have to do the resizing process, bleaching, the mercerizing process. These are all pre-treatment process, which are very intensive consumers of energy, electricity, but mainly thermal energy in the form of steam or natural gas for itself. It is also a very intensive consumption of chemicals and also of water. And of course, if we have all of these inputs, we also have the outputs, the associated outputs, the wastewater generated, the air emissions associated to the production of thermal energy and the waste. Then we go to the dyeing process. Of course, as some of you know, the dyeing of a textile can be performed in the different steps of the production process. We can have dyeing of the fibers, but we also can have dyeing of the yarn, dyeing of the fabric, and also dyeing of the garment, the final product. But usually for the generic textile production process, the dyeing is located here in the finishing process. And the dyeing also consumes lots of energy, especially thermal energy, chemicals, and water, and with the associated outputs. Then for some products, we also have the printing process. And the printing process also consumes electricity, thermal energy to perform the drying after the printing process, the chemicals and water, and also with the associated outputs. And then the finishing processes, which can be mechanical, and the mechanical finishing process only consumes, the main consumption is from electricity and chemical, and the chemical finishing, and in the chemical finishing we also have thermal energy and chemicals and the consumption of water. And in the end of the production chain, we have the apparel or the confectioning of the products. This is the process with a lower environmental impact, because we have mainly electricity consumption, and in some cases for the finishing, for the ironing of the for the ironing of the products, we also have the consumption of thermal energy if the steam used in ironing is produced in a boiler, and the associated outputs are the waste and the air emissions in the finishing. Again, if the steam used for ironing is produced in a boiler. But the consumptions here the energy consumptions here are very low compared with the other steps of the production process. So usually the apparel or the confectioning process is the process with with less environmental impacts. Then we can have also the transport and distribution. Of course, we can have also the transport between the production of raw materials to the beginning of the manufacturing process, and also in the manufacturing process, because usually in the textile sector, the different sub processes are performed in different facilities. The yarn is produced in a company, and the weaving is produced in another company. The white treatment is produced in another company, and the confection in other. Or we also can have some vertical companies, but the most common is that the different steps of the manufacturing process is performed in different facilities. So we also have transport between those facilities. But okay, we are speaking about the transport here after when the product is done and is going for retail and for distribution. And here, of course, we have the electricity consumption of the retail stores, and we have the fossil fuel consumption associated to the transport of the materials of the products, and with the resultant emissions that are the emissions of pollutants to air associated to the combustion of the fossil fuels of the transport, and also the waste generated in the retail stores. After the retail and transport, we have the use phase of the products, and here the main environmental aspects are the electricity consumption and also water and chemical consumption associated to washing the products, the textile products, and also to washing and after that to drying when the drying is performed in machines and not at the sunlight, and the ironing of the textile products. These are the main environmental aspects associated to this stage of the life cycle. And after that, we have the end of life of the product. And nowadays, with our linear economy, it is what we have nowadays. Of course, we are trying to move to a circular economy, but what we have nowadays, and especially for the textiles, is a linear economy. And so the main ends for the textile products are the landfilling, which implies the land use, the use of a very big surfaces, and we have the emissions of pollutants to water and to air. Or when the products are not landfilled, they usually they are incinerated, and this way of end of life as promotes the emissions of pollutants to air, including some very components with a high toxicity. But in the other side, this process of end of life as an environmental credit, which is the energy production associated to this process. But of course, what we intend is to move to a circular economy, so we can have different end of lives for the textile products, which is the reuse of the textile product, which is the method of end of life, which has the lower environmental impact, and it contributes to replace the production and the extraction of virgin raw materials. And it also, of course, if you are reusing, we avoid the production of raw materials, and we also avoid the manufacturing of those products again. And when we are talking about the recycling, we avoid the production of new virgin raw materials, but we don't avoid the manufacturing process associated to those products. And we also have as mechanical recycling only consumes electricity, which is the main environmental aspect associated to mechanical recycling. If we are speaking about thermomechanical recycling, like the recycling of polyester from bottles, we are speaking about huge consumptions of energy and such electrical and thermal. All of these recycling methods has the advantage of substitute of replace virgin raw materials. And then, of course, the chemical recycling, which is supposed to be the recycling method which has more environmental impact, with energy consumption, electricity, and thermal energy, and also the consumption of chemicals. but it of course contributes to the substitution of to the replacement of virgin raw materials. And this was the introduction that I intended to do about the life cycle of a textile product, because I believe it's important for what we are speaking next, which is the life cycle assessment. And the life cycle assessment, has a lot to be with inputs, environmental inputs and environmental outputs of the different life cycle stages of a product, as we will see after. So, starting with the life cycle assessment, let's speak a little bit about the concept and the main applications of life cycle assessment. And what is life cycle assessment? And as it is defined in the standard, in the ISO standards, life cycle assessment is a methodology to assess the potential environmental impacts associated with all stages of a product life cycle, from the raw material extraction, passing through the material processing, the manufacturing, its distribution, use, and end of life. And this is the definition of life cycle assessment in the standards. Is a methodology to assess environmental impacts. This methodology is applicable to products, to activities and service, to economic sectors, to organizations, also to territories, like a country. We can perform a life cycle assessment of a country, but it is mainly used to quantify and to determine the environmental impacts associated to products. It's mainly used to products, this methodology. So, and what's the objective of the life cycle assessment and the life cycle assessment standards? Their objectives are to help to organizations to identify the environmental aspects associated to the production of a product or a group of products, the environmental aspects that those organizations can directly control. And if you remember the introduction, the introduction of the environmental aspects, for example, a spinning mill, what can they control? They can control the raw materials that they buy, and they can control their consumption, their electricity consumptions. So they can act in the reduction of the electricity consumptions to reduce their environmental impacts, and they can also act in the types of fibers that they are using. But it helps also to companies to identify to identify the environmental aspects that they can influence upstream and downstream of the value chain of their products, which is they can influence. They can, if they buy less conventional cotton and they buy more organic cotton, they are influencing the an activity upstream of their company. If they are using, if they are buying, they are buying more. They are buying more in local, or they are subcontracting services in local, in the local, in the proximities. They are also affecting. Activities upstream or downstream their value chain, and that can. And this is the main objectives of life cycle assessment, and it also has a system perspective, which is the main goal or the ideal life cycle assessment must include all stages of the life cycle. Of course, it is not always like that, as we will see later in these presentations. Sometimes we perform the life cycle assessment only to the factory gate, only to the intermediate product, and we do not consider some phases of life cycle assessment. But the idea is to the life cycle assessment as a system perspective to include all the steps in the products, in the system of products. And what it is used for. There are two main drivers to perform life cycle assessment studies. The first one is more internal, is more for internal knowledge. If a producer of a certain product wants to know what is the environmental impact of its products, it can only know it can be the only goal of a certain company is to really know what's the environmental impact of a certain product, or to identify which stage of the product which has a higher environmental impact, and act in that stage of the production processes to decrease the environmental impact of that product. But usually the life cycle assessment studies are made for external communication, and for external to support some commercial claims about the sustainability of a product with data, with data, with a quantified methodology. And but this is where the life cycle assessment can be more tricky, because if we want to make some commercial claims and we want to compare our products with other products, not other internal products, of course, if you want to compare two of your own products, it's okay, it's more relaxed. But if you want to compare with other products from other manufacturers, it's tricky, because there are lots of additional requirements, like, for example, a critical review for a panel of specialists is needed when we want to communicate this kind of commercial claims. So, and of course, the main applications of life cycle assessment are product development to produce better products with and lower the environmental and decrease the environmental impacts of those products. Process development, of course, if we know in the production of a certain product what are the processes that have more that are more critical in terms of environmental impacts, we can act on those processes, and we also can compare the processes that we are using with other processes to check if it's possible to reduce the environmental impact of our product by substituting a production processes. Decision making, of course, if we are producing a shirt and we have two different raw materials, we have the choice between two different raw materials. We can perform a life cycle assessment of those two different raw materials to choose between them. And of course, for marketing purposes, to develop environmental product claims, and also to be a base for environmental product declarations, and to define objectives for reducing environmental impacts. the main advantages of the life cycle assessment methodology is as I said before, the original idea is to have a cradle to grave approach. So putting in our product system all the stages of the life cycle, which is important to not because when we are comparing a product, of course, if we perform a life cycle assessment only to the factory gate and we do not consider the use or the end of life, and then one product have a recyclability is more recyclable than the other. Of course, those aspects have also to be considered for us to say if a product is has a lower or an higher or a lower environmental impact. And we know that when we perform life cycle assessments from cradle to gate only, we are not considering all the aspects of the life cycle of that product. It's also another advantage is the multi-criteria analysis. So in a life cycle assessment, we do not analyze only. Of course, we can analyze only one aspect, and when we perform carbon footprint studies, we are only analyzing one aspect, which is the emissions of greenhouse gas to the atmosphere, but usually we analyze more environmental aspects. It's a quantitative analysis. It's not only to say my product has lower environmental impact because it has. No, we have to make calculations. We have to quantify those environmental impacts, and it prevents the transfer of environmental products, for example, from one stage of the life cycle to the other. But for this, of course, we need to consider the cradle to grave approach. But this methodology has also some weaknesses. Especially associated to the time required to do such an assessment and the associated costs. It's a very time-consuming methodology, mainly in the inventory part, as we will see later, because the data collection associated to the to the life cycle inventory is very time demanding, and of course time is converted in money. It's also the costs associated to this kind of assessments are still a little bit high. The lack of data, of course, it's not easy. Of course, it's more or less it's easier to find data for the manufacturing process. It's for the manufacturing process of especially when we are talking about textile products, it's more or less easy to achieve data for that phase of the processes. But when we are talking about the data from the upstream or downstream activities, it's not easy to find that. And of course, when we are speaking about the use phase, for example, usually in the use phase, the use phase is modeled with assumptions, making scenarios, and not with real data, because of course we don't know exactly when we produce a shirt or a pair of jeans or a pair of shoes. We don't know exactly how those products will be used and how many times they will be washed and ironed. So usually the use phase is modeled using scenarios of utilization. and of course the relevance of the results, but the relevance of the results is especially associated to a good definition of the goal and the scope of the study, as we will see in the next chapter with the phases of an LCA study. So an LCA analysis, phases of an LCA analysis. The general framework defined in the ISO standards for an LCA analysis comprises four main stages. The first is the goal and scope definition, where we think what do I want to why am I performing a life cycle assessment? What are my objectives? What do I need these results for? It's for me to understand my production processes and what the critical points of my production processes. It's for an external a commercial claim. We want to compare with other similar products. And this we have to define in the goal and scope definition stage, which is a planning stage. Here in that stage, we need to define what we want to do and how we will do it, and what are the results that we want to achieve with this study. Then we pass to the inventory analysis, where is a stage mainly for data collection, for the data that I need to make my life cycle assessment study. We have to collect it. So it is in the inventory analysis that we collect that data and we build the model of our product. And then in the third step, we pass for the impact assessment. And here in the impact assessment, it's where we convert all the data that we collected, and then we treat it, and then we attribute it to the system, the inputs and outputs, and then it is when we convert that inventory data in the environmental impact indicators for the selected environmental impact categories. For example, if we want to know what's the indicator of the climate change or the global warming potential of our product, which is calculated in kilograms of CO2 equivalent. So later we will see a little bit more in detail what are these environmental impact categories and indicators, and also the methods to do the impact assessments. And the last stage of the life cycle assessment methodology is the interpretation. And here is where it is where we look at the results that we obtained, and also with the results and the methodology that we have, and we compared with the goal and scope what we have, what were our objectives. And as you can see in the figure, life cycle assessment is an iterative process. So usually what our first objectives are not what we have at the end, because there is an iterative process is that when we check the results, and we have when we check the results, we have to analyze them, and we have to see if they make sense, and if they don't make sense, we have to go back behind to some of the other stages and reformulate as needed. So started for the goal and scope definition. As I said before, the goal and scope stage is where we plan what we want to achieve with a life cycle assessment study and how we will do it. So the goal and scope, we must establish the intended application of the results that we achieve in the life cycle assessment, the reasons for carrying out the study, why. So why am I doing this study? The target audience, what means that means to whom the study results are intended to be communicated, if the results are only for internal consumption, or if we intend to communicate the results externally, and whether the results are intended to be used in comparative statements for public release. And this is important because, as I said before, if we want to make comparative statements for public release with third-party products or with other products that are not our products, there are additional requirements for this for the life cycle assessment, and the main additional requirement is the critical review, which is needed, and it is a critical review not only by a specialist but by a panel of specialists, at least 3 specialists that will analyze all the steps of the life cycle assessment and provide a review of the study. The scope. The scope of the life cycle assessment study must address those items: the product system to be studied, the functions of the product system, and the functional unit, the system boundary, which means what we will have inside our product, what steps, what processes we will have inside of our product system. The allocation procedures, if we have allocation, and we will see later what is allocation for those who still don't know what is allocation. The selected impact categories and impact assessment methodology. But it also has to address the data requirements, the assumptions. If we make some assumption that can have important that can be important to the final results, we need to describe in the scope of the study what is that assumption, the main limitations of the study, and also the data quality requirements, and the type of critical review, if any, and the type of and format of the report of the study. So the functional unit of a life cycle assessment study, what it is. As it said in the slide, the functional unit defines the quantification of the identified functions or performance characteristics of the product. And what is important, the main purpose of a functional unit is to provide a reference to which inputs and outputs are related. Of course, and as you can see here, when we have a result for a carbon footprint or for a global warming potential of 2.5 kilograms of CO2 equivalent, it has to be referenced to a unit, for example, of a shirt. This 2.5 kilograms of CO2 equivalent, but it can be referenced to a shirt. But if we are making a life cycle assessment study of a fabric, of a woven fabric or a knit fabric, maybe that reference will not be one shirt, but it will be 1 square meter of fabric. And if we are performing a life cycle assessment of a fiber or a yarn, usually the functional unit is a kilogram of or a ton of material. It's in weight. And the functional unit is very important for what? It's very important to ensure the comparability of the life cycle assessment results. And the comparability is very important when we are evaluating different systems, which means we can have products with the same function, but their production systems and their system products are different. And it's very important to have to define a good functional unit to ensure that the comparisons are made on a common basis. And we can have here an example. For example, and this was a situation that we had in some years ago with during the pandemic time, where our company started to produce lots of masks, of reusable masks, and then it was we had the need to compare the environmental impact of some masks, of some reusable masks that the company were creating with the disposable masks that were in the market and coming from China. And then, of course, with that goal, the comparison between the disposable mask and the reusable mask, the functional unit could not be, the functional unit, it would make no sense to compare one disposable mask with one reusable mask. So the functional unit on that case need to be the use of a mask a number of times, and usually 20 times or 15 times. It was dependent on the useful life of the reusable masks. So in that case, the functional unit never could be one mask or a quantity of masks, but the function. It had to define the function of the product, and the most correct functional unit for that case was the use of a mask 20 times. So, and in the case of the disposable mask, a use of a mask 20 times means to produce 20 masks. And of course, with the reusable mask, it was only the production of one mask. So, and we have here one example. It's of a life cycle assessment study that is that is also that is accessible in the internet. Here, as an example of a goal definition, what am I going to do? And the objective was to determine the environmental impacts of cotton shirts production from cradle to factory gate. And the reason for carry out the study was to understanding the environmental impact and the outpoints of the life cycle, which means to understand what were the life cycle phases or the production phases which have more environmental impacts. And the defined functional units are 1,000 shirts. Here, as it is a cradle to gate study, we do not need to define specially the function of the product. So, and after that, we can speak a little bit about system boundaries, which are also very important for a life cycle assessment study. And in this case, a system boundary defines which unit process we will have we will include in our system product system. Ideally, the product system should be modeled in a way that the inputs and outputs of the boundary are elementary flows, and we need to define the life cycle stages and the unit process to consider. And of course, when we speak about system boundaries, we also need to define if we will have some exclusions of some criteria for exclusions. For example, if we are not considering flows, material flows or waste flows that will represent less than a defined percentage of the mass of the final product, or if you are excluding some inputs that do not significantly affect the final results. In any case, of course, environmental relevant processes should never be excluded. And when we are speaking about system boundaries, we speak about some different approaches, as I said before. Ideally, the ideal life cycle assessment is the holistic life cycle assessment shall consider all the phases of the life cycle: the raw materials, the manufacturing, the use, and the end of life. And this approach is what we is known as cradle to grave. And cradle to grave means cradle is from the birth of the extraction of the raw materials, and grave is the end of life of a product. And all inputs and outputs considered for all phases of the life cycle. But sometimes it's not like that. Sometimes, and we see a lot of this kind of studies, which are the cradle to gate approach, which is a partial an assessment of a partial life cycle of the product, usually between the raw materials extraction and production to the factory gate. If it is a confection, it's to the production of a T-shirt or of the pants. If the factory gate, it's in the weaving mill or the wet treatment plant. It can be a square meter of a fabric. If the factory gate is in the spinning mill, it can be 1 kilogram. It can be to the production of the yarn. Usually, in this approach, in the cradle to gate approach, the use phase and the end of life are not considered. Um, uh, those kind of studies, the cradle to gate studies, were performed for in the last year for the production of environmental product declarations. But nowadays, the standards for the environmental product declarations, the specific standards, are obliging to perform cradle to gate studies to obtain the environmental product the declarations, and not only cradle to gate as it was the normal in the past years. And we also have an approach which is not very common. It's I should say which is gate to gate, which is an approach which considers only one phase of the life cycle, and usually it's one phase of the manufacturing process, and is an approach that is only used to compare two processes, two production processes to obtain the same product with the same raw materials. When of course we can say that if the raw materials are the same, the product the produced product is the same, which the same use and the same end of life. Of course, we can exclude that and only focus on the process under analysis to assess the environmental impacts of it. But as I said before, it's not very common. It's not a very common approach. And then, we were speaking about, of course, linear economic perspective before, and then we have a specific type of cradle to grave, which is the so-called cradle to cradle. In this case, the end of life of the product is a recycling process to obtain that which produce raw material for another process for the same process. It can be for other process or for the same process, but this is the typical circular economy approach. So, but when we define the system boundaries, um, of course, according with a standard which and after we define the approach that we will follow, we shall consider the obtaining of raw materials, the inputs and outputs of the main manufacturing, of the core manufacturing process, the manufacturing process, of the distribution and transport, the production and use of fuels, electricity and heat. Of course, if we are using electricity, that electricity shall be produced somewhere, and the production of that electricity has environmental impacts, so we shall include in our product system. If we are using fuels, mainly for transport and also for our production process, those fuels must be produced somewhere. So we need to include the impacts of that production also in our system boundaries. And for the cradle to grave studies, the use and maintenance of products, the final destination, the recovery, the recycling activities, and of course the manufacturing of the auxiliary materials. And regarding the system boundaries, we can check that example, which is the example that we see before of the production of the shirts, the 1,000 shirts, and what is included in the system boundaries of that example. It's included, as we can see, the agricultural phase. It's where is the cotton used for the shirts is produced, the yarn production phase, the fabric production phase, and the shirt production phase, the confectioning phase. As we can see in that case, the different stages are performed in different locals. So we have transport between those locals. And we can see there it is stated the inputs and the main outputs of each of the phases of that system product. Then also in the goal and scope, we must define the data quality requirements. Which is which kind of data we will use for the life cycle assessment study. Usually, if we are when we are performing, as we will see later, but if you are performing a environmental product declaration, environmental product declarations have specific standards, which are called the product category rules, that define the characteristics of and the quality of the data that we have to use in those studies. But we feel we are not performing a life cycle assessment study with a specific standard or with a product category rule. We must define for ourselves the quality of the data, and it has to be with the objectives of our study. Of course, if we want to make if we want to communicate, and if we want to make comparative comparative claims, we must use high quality data and not low quality data. And that's because the description of data quality are important to understand the reliability of the study and to interpret and for the interpretation of the results and a proper interpretation of the results. So the characterization of the data quality must establish the time coverage of that data. For example, if we are using data with no more than 5 years, and average values or annual average values, which represent the state of the art of the production process of that product. The geographic coverage, the geographic coverage, it's important where that data comes from, and also the technological coverage. If we are using data from current state-of-the-art process, the best available technology, or if we are using data of old technology with 20 or 30 years. That is also important to be stated in the definition of the data quality. The data related to input flows. It's of course the consumption of raw materials must be there. The consumption of auxiliary materials must be there also. The consumption of energy, both electricity and fuel, and of course the water consumption. The data related to output flows, it has to be there. Data of the production of products and byproducts. If the system has byproducts, it's not very common in textile, but in other cases, in other sectors, it's very common. Like for example, the chemical industry, it's very common to the same production process results in several products like diesel and gasoline and liquefied petroleum gases in the refinery process. Of course, the emissions to air must be there also. The emissions to air, namely the emissions of carbon dioxide, the emissions of NOx, SO2, carbon monoxide. The emissions to water, the nitrogen, the phosphorus, the chemical oxygen demand, the solid waste generated by the system products, and also other output, other flows like land use, like radiation, this kind of stuff. So, but when we are speaking about data, we can perform life assessment studies with a mix of different data. Ideally, the ideal life cycle assessment study would be based only in primary data, in specific data collected on site based on average annual values, But that was the ideal case. Most of the times we have a combination of primary primary data and secondary data. And in primary data, we have the data collected on site, specific of that site. We also have some educated assumptions, which means that by experience we can make some assumptions, some realistic assumptions of consumption and emissions. But we also have the so-called secondary data or generic data, which is data from mainly from bibliography or commercial databases available in the market. And the most known are the EcoInvent database and also the Sfera database. And we can also have some proxy data, which are simulations. But of course, as we are going down in that graph, we are decreasing the quality. The primary data is always data with more quality than secondary data. And ideally, of course, in the again, when you are speaking about environmental product declarations, in most of the product category rules for environmental product declarations, is stated that when we are speaking about the core production process of a product, and for example, for the textile process, the production process from the production of yarn to the production of the shirt must be based in primary data. And the upstream and downstream activities that we can use secondary data if we do not have access to primary data. But of course, the LCA standard, the ISO 14040 and ISO 14044 do not specify the quality of the data. Only the specific standards associated mainly to environmental product declarations or to the environmental to the product environmental footprint, as we will see later. Those product category rules define the data quality that we shall use in a life cycle assessment study. So I already said that in the previous slide. So the best practices for data sources. The process that contributes mostly to mass and energy flows and to with more relevant impacts must be based in primary data. All the background processes can be based in secondary data. Okay, and then one of the last phases of the life of the goal and scope. The goal and scope definition is the selection of the impact categories. We must select the analyzed impact categories, the category indicator, and the characterization methods and models must be included also in that part of the LCA study. And of course, the selection of impact categories depends on the objective of the study, the available inventory data, and the maturity of the impact assessment methods for those specific impact categories. We will check this more in detail later in the impact assessment phase. But okay, we also have to define those we also have to define this in the goal and scope definition. So here is only some LCA impact assessment methods, which were the most used. Of course, this figure is from 2018 or 2019. Now it can be a little bit different, but these are the most used impact assessment methods. and just to have in mind that the recipe, the IPCC, of course, the IPCC is only for the determination of global warming potential, and also the CML uh, are the most used methods on those days. Now I believe it's not very different. Maybe for the toxicity, the use tox is now the most used method, but the distribution must be similar with that. So now I will start with the life cycle inventory, but as it is 10:30, I will suggest to make a 10-minute pause, and then we will start. We will start again, and at 10:40. Okay.
Okay. Thank you, Luis. I think I don't know if Helena Ferreira wanted to talk.
Okay. If you have any doubts, please.
Okay. If anyone has any doubts, please write the hand. If not, we will just proceed to the short break.
Okay.
Okay,
So
Luis.
see you in 10 minutes.
See. Thank you.
Hello, Raquel. Shall we proceed?
Hello, I think we can proceed, yes.
Okay. Okay, we have already seen the first phase, the first stage of the life cycle assessment studies, which is the goal and scope definition. Now we will go to the second stage, which is the life cycle inventory. And as I previously said, the life cycle inventory is nothing more than to collect the data, the necessary data, to calculate the environmental impact, or to determine the environmental impact of our products. So we need to, in this phase, we collect the information and the procedures to calculate and to quantify the input and output data of a process, of all the unit processes defined in our system boundaries, such as the energy consumption, the water consumption, the materials, and the associated emissions. Then we collect that data for each and every process inside our system boundaries, but then we have uh, to refer to relate that information, that values, to the functional unit defined in the scope of the study. So according to the standard, the life cycle inventory starts with a data collection. Then after we have the collected data, we need to validate it, and that's very important to validate the data, because if we put the wrong data on the model, of course the results will not be good also. Then when the data is validated, the data for all specific processes, we need to relate that data to the unit of the specific process, and then to relate that data to the functional unit of the study. Then we can perform the aggregation of the data, which is to sum the same data for each of the processes, and to calculate the inventory. And then we refine the system boundary if it is the case. If we don't need to refine, we proceed with the same system boundaries, and then we have the inventory completed. So when we speak about data collection, it's what we have been saying. What I have been saying is to collect the qualitative and quantitative data for each unit process, the data related to inputs and outputs, and that data it's meant to model those unit processes, and together they will model our system product, the system product of our life cycle assessment study. When we are collecting data, we must classify that data. We must classify the energy inputs, the raw material inputs, the auxiliary inputs, and other physical inputs. And also we have in the outputs to classify the main product, or the main products of our system, and also the byproducts and the waste, and the emissions and discharges, the emissions to air, the discharges to water, and the waste generated, and also other environmental impacts. But the first three, we need to classify the data in those three items. Then after after the data collection, we must validate it, and that's very important, because sometimes even if we are measuring, of course, if data is measured in this specific collected data, it's more reliable. But when the data is not mainly when the data is not measured, we need to validate it, and the validation must involve mass and energy balance and energy balances to each of the unit processes, and also to other strategies. And the experience is also very important when we look to the data of a specific unit process. Then after the data is validated, we must relate the data to the unit process. And this, for example, we have here the data from the production of a rib in a knitting facility, and we collect the data, and then we related the data to the unit process, and in the case it's with 1 kilogram of rib. And then, of course, for each unit process, the appropriate flow must be determined, and the quantitative input and output data of the unit process shall be calculated in relation to the flow, to the appropriate flow. That in this case, it was 1 kilogram of rib, but it could be 1 square meter of rib. And if you were talking about yarn, it could be 1 kilogram or 1 ton of yarn. Then we need to relate the data to the functional unit, and not to the unit process, as it is stated in the slide. Is to relate the data to the functional unit. We must know, we must build based on the flow chart of the processes, of all the unit processes. We know what is our reference flow, our functional unit. That was in the case presented here. It was a t-shirt. So for the production of that t-shirt was 266 grams. We needed 352 grams of fabric, and we know to the production of that fabric we needed 381 grams of yarn, and to the production of that yarn we needed 496 grams of fiber. So, and this is to relate the data of each unit process to the functional unit, that in the case was a t-shirt. And then we pass to the aggregation of the data, and of course we shall only aggregate data which represents the same environmental impacts. If they don't represent the same environmental impacts, of course we can only aggregate data. We can only aggregate air emissions of carbon dioxide with air emissions of carbon dioxide of the other process. We shall not aggregate the data for different environmental impacts. Of course, we cannot aggregate data from we cannot sum or aggregate an emission to air with an emission to water. They are different. They have different environmental impacts, so that data could not be aggregated. Okay, and then when we have the data collected, validated, in some cases we can refine the system boundaries. Mainly in what stands for the exclusions. We can check. Okay, we have the data. We can see that this flow has a very low impact on the whole system product, so we can exclude this flow, and then we are this and these are the refinements of the system boundaries that we can perform after we have the inventory data collected and treated. So it's what is said here. We can also perform the sensitivity analysis, which lead to the exclusion of life cycle stages and or even unit processes when we see they don't have any significance in the final results. And also the inputs and outputs. And we can always exclude, but we can also include if we see that other unit processes or other flows that were not initially included in our system must be included because they have significance. And this is one way in which the life cycle assessment is an iterative process. And then we pass to the allocation. And what is the allocation? The allocation happens when we have systems with multifunctionalities. For example, a system that produces not only one product but several different products. And as in the example that I gave before, for example, the refinery, a refinery, an oil refinery, which at the end of the distillation column, we obtain the naphtha, and we obtain diesel, we obtain gasoline, we obtain liquefied petroleum gases. So we obtain several products, and to what products, what percentage of the environmental impact shall be allocated to each of that product. And this is a situation that happens regularly in the chemical industry. In the textile industry, is not so common. But in this case, in the case of this project, it's also important, like we will see later, because we are leading also with recycling, and recycling also has some special things about allocation. But what the standard says about allocation is that first, whenever possible, we shall avoid allocation. So and we can avoid allocation, dividing the unit process to be allocated in two or more sub-processes, and collect the input and output data related to the sub-processes. This can be done sometimes, but most of the times it's not possible. It's not possible to divide a unit process where we obtain more than one product and divide that process in different sub-processes for each of the products. And the other option is to expand the product system to include the functions related to the byproducts. For example, if we are performing a life cycle assessment study to a product, and in the same system we obtain a byproduct, not do the allocation if we include in that system a product system for the obtaining of the byproduct, and then use that byproduct and then get an environmental credit for the substitution of the production of that byproduct. There are the two ways that we have to avoid allocation. However, sometimes it is not possible to avoid allocation. So we need to perform the allocation of the products, and one of the methods is to allocate the environmental impact to the different products based on physical properties, based on a quantity of the different products that are produced in the same system products. This is one of the options, and it's very common in the refinery systems to allocate the environmental burdens to the different processes based on the quantity, on the amount of product that is produced in the distillation column. But sometimes that's not the ideal, because sometimes we have a system product that produces a byproduct in a not excludable quantity, but the physical relation is not ideal, because the economic value of the byproduct is residual, and our production processes, our system product is to obtain the main product and not the byproduct. In that case, usually we can use the economic value of the products to allocate the environmental impacts. And if it's the case of the difference in value, it's very significant. We can allocate based on the economic value. So we always have to check and find the best solution for each system product. These are the recommendations of the standard, but we always have to find the right solution for each specific system product. So, and we also have allocation in recycling, which is also important, because when we have a system product, which in the figure is the system product one, or life cycle one, and then at the end we have a product that is recyclable and used as a raw material for another system product, for another life cycle, the life cycle 2 in the case. We have the recycling process between them, and to each of the system products shall we allocate the environmental impacts of the recycling process. And there are two main approaches in recycling for allocation, and the most used is the recycled content, or the cut-off approach. And this approach says that in that case, with that approach, the environmental impacts of the recycling process shall be attributed to the life cycle 2, because the life cycle 2 will also have the environmental credit of replacing some of the virgin raw materials. So it must has also the impact of the recycling process associated to the byproduct of life cycle 1. The different case is if you can if you can use the recycled product directly in your system product. Then we usually use the closed loop scenario, which is after the recycling, the product gets in the system the system product one, and in that case we expand the system of life cycle one to include the recycling process, and the environmental impacts of the recycling process are attributed to life cycle one. These are the two main approaches. Can some other approaches can some different approach can be followed, but these are the most common, and the most common is really the cutoff approach for cases where the product is not used in the same system product. If the product obtained by recycling is used in the same system product, the closed loop scenario may be may have more advantages to be used. So then, when we are at the end of the life cycle inventory, we have something like this, which is for the example of the 1,000 shirts. You can see in the different columns the different unit processes, aggregated unit process, the cotton production, yarn production, fabric production, and in the fabric production is the wet treatment is included, and also the shirt production. And for each of these unit processes, you can see the input flows, which are in the table on the left, and the output flows, which are in the table of the right. And what you can see is that most of the water consumed in this system product is in the cotton production. It's in the cotton production stage. Regarding the electricity, is most consumed. As I said, if you remember the first slides of this webinar, when we spoke about the environmental aspects associated to yarn production, to spinning. As I said there, spinning is very electricity intensive, and we can see that here in the yarn production column, which is the most electricity intensive consumer. Then we have the natural gas. Of course, the natural gas is mainly associated to in this case to fabric production, because in the fabric production here includes all the wet treatment of the process. And after that, you can see the cotton production. You have the consumption of fertilizers and pesticides. Within the fabric production, in the wet treatment, we have the consumption of the chemicals, the dyes, the salt, the detergents, and all of the chemicals used in the wet treatment. And also in the shirt production, but in lower quantities, also some chemicals that are used. And as in the emission side, we can see that, of course, the wastewater is mainly generated in the wet treatment phase. And then we have also the emissions to air, the carbon monoxide, SO2, NOx, which are mainly associated to the fabric production. Again, to the finishing process. So this is an example. Usually, the inventory of a life cycle assessment study is always a table like this, similar with this, with one side the inputs and the other side the outputs associated to each of the stages of the life cycle. And as I said, and after the life cycle inventory, we have the life cycle impact assessment. And the life cycle impact assessment, in that phase, we that phase is intended to assess the significance of potential environmental impacts from the inventory results. So all data collected and aggregated during the inventory, the material and then energy flows, and also the emissions are associated to the environmental impacts that we intend to calculate. To we have already selected the impact categories that we decide to assess in the study during the goal and scope definition. And here we will relate the inventory data to the different impact categories. For example, if we have the emissions of carbon dioxide, we will relate those emissions to the impact category, which is the climate change. And if we have the emissions of nitrates during the cotton cultivation, we will associate those emissions to eutrophication, which is like an impact category that measures the amount of nitrous substances in the water or in the soil. And of course, and the impact categories and then that potential shall be calculated, and then we can weight the results of the different impact categories to obtain a single value for the environmental impact of that product, which is in the case of textiles can be important, because if we are comparing different raw materials, for example, if you are comparing cotton with polyester, there is always a doubt that come across, because okay, polyester have more impact in climate change because it consumes more energy and it produces more air emissions. So the impact of polyester in climate change is higher than cotton. But for the other side, cotton is much more water intensive. The water footprint of cotton is much higher than from polyester. So what to what category shall we attribute the higher percentage, the higher importance? It's a decision that the author of the study can shall make if they want, of course. If the author of the study want to weight the categories, otherwise they will only put the values of each category, and will we will make an interpretation based on the different categories and not of a weighted value. But okay, life cycle assessment, as we see there, I believe that that image helps to explain what I said before. We have the life cycle inventory. Well, we are there when you have the CO2 emissions. We attribute the CO2 emissions to climate change. course, if you have emissions of toxic substances, we attribute it to toxicity category, impact category. Land occupation, we attribute to a category land use, and the water inputs to water use, and of course we have other impact categories and other emissions and other inputs determined within the life cycle inventory. But this is what we make in the life cycle in that phase of life cycle assessment studies. According to the standard, the main phases of the life cycle impact assessment is a selection of impact categories, category indicators, and characterization models, and we will see what it is each of these things. The assignment of the classification, which is, as we said before, to relate the inventory results to the specific impact categories, and then the calculation of the category indicator. Those are the mandatory elements for a life cycle impact assessment. But then we have some optional elements that we can perform, like, for example, a normalization, which is a calculation of the magnitude of the category indicator with reference to a reference value, and to aggregate and weight the results. So here, that phase, the selection of impact categories, category indicators, and the characterization model. This is what make the life cycle assessment method. Of course, that selection must take this selection must take into account our goal, what is defined in our goal and scope. And there are some cases like the environmental product declarations, or if we are making a study of product environmental footprint, where the impact categories are already defined in the standards, in the specific standards, the specific product category rules for a specific product. And if we are doing a study like that for environmental product declaration or a product environmental footprint, we must analyze the impact categories that are stated on those standards or on those product category rules. And that the definitions of the impact category. What's the definition of impact category? Impact category is a class that represents the environmental issues worthy of concern, to which the results of the life cycle inventory shall be attributed. And some of the most known impact categories are the following: climate change, or global warming potential, or carbon footprint. I believe almost everyone already heard about this impact category, but we have also other impact categories like acidification, which is related to the emissions of acid substances to the atmosphere, mainly in what concerns to sulfur substances with sulfur. The eutrophication, like I said, which is mainly associated to the emissions to water and soil, the emissions of nitrates and phosphates and other phosphorus components and nitrogen components. And then we have also some categories which are related to the depletion of resources, and we can have the depletion of fossil resources, like which is associated to the consumption of natural gas and oil, and also to other category impact category, which is the toxicity, which is, I believe, as far as I know, very important in this project, which is related to the release of toxic substances to the environment. And then we have impact category indicator. And what it is, the impact category indicator is a quantifiable representation of an impact category. And for example, for the global warming potential, we can have the global warming potential 20 years or a global warming potential 100 years. And the characterization factors are different for these two impact indicators. And of course, those impact indicators are associated to the methods used for the life cycle assessment. And then, of course, some of the main life cycle assessment, the most used life cycle assessment methods, like we saw in one previous slide. One of them is the CML. Which is a method developed by the Institute of Environmental Sciences in the University of Leiden, and it is a generalist method because it is a method that allows to calculate several impact categories, environmental impact categories. Then we also have another the recipe method, which was developed also in the Netherlands by the National Institute for Public Health and the Environment, and one consultancy, which is a pre-consultants, and the University of Leiden. It's also like the CML generalist method, which allows to calculate different environmental impact categories. And also, of course, the environmental footprint, which is a method developed by the European Commission, as we will see later a little bit more in detail. But it's also a method that allows to assess several impact categories. And then we have some also methods for impact assessment that are focused on specific impact categories. Like, for example, the IPCC method. The IPCC is an intergovernmental panel for climate change, and which regularly release the assessment reports with emission factors for the greenhouse gas, where the greenhouse gas is defined in the Kyoto Protocol. And of course, this method is only applicable to climate change or to global warming potential impact category. And we also have a method now, I believe the most used method to assess the toxicity. The toxicity, which is the use tox method, which was developed by the United Nations Environment Program, and it assesses human toxicity and ecotoxicity impact categories. Here it is again the same figure. Okay, we already saw this figure. And here is some resume of some existing methods and which impact categories those methods allows to calculate. For example, as you see, the CML baseline allows to calculate a very big quantity of those impact categories: acidification, climate change, ecotoxicity, resource depletion, eutrophication. The same with the recipe method, as we saw before. The method that is there defined as ILCD is nothing more than now the environmental footprint method. And then we have the use stocks, which only calculates the impact categories associated to toxicity. And of course, there are others. For example, for water consumption, we have the aware method, which is also specific for the water depletion impact category. So as a resume, for example, for global warming impact category, global warming, we can have an indicator like global warming potential 100 years, and a method, the IPCC, which is calculated in kilograms of carbon dioxide equivalent. For eutrophication, we can have an indicator called marine eutrophication, and we also have freshwater eutrophication, and we can calculate it using recipe in kilograms of phosphorus equivalent. For water depletion, we can have an indicator of water deprivation, and using the method AWARE, which is calculated in cubic meters of world equivalent. And toxicity, we can assess the human toxicity with the method use-tox in units, in cumulative toxic units for humans, which is a unit that are measured that impact that indicator of impact categories. So in the column in the left, impact category; in the middle, the indicator of the impact category, and the method to calculate that indicator. After the selection of impact categories and indicators and methods, now we have to make the classification, which is a correlation between the life cycle inventory results to the different impact categories. This is a qualitative procedure only, and as we can see in that table, for example, for the climate change, we attribute the emissions of carbon dioxide to air, the emissions of methane, and the emissions of nitrous oxide, which are the sum of the greenhouse gas. The greenhouse gas is defined in the Kyoto Protocol. Then to acidification, we can attribute the sulfur dioxide, the NOx, the NH3, and the sulfuric acid. Freshwater eutrophication, we attribute phosphorus and the other phosphorus compounds. Marine eutrophication, we attribute nitrogen and other nitrogen compounds. For example, for fossil depletion, we attribute the consumption of natural gas, of petroleum. And this is what we mean by classification. Then, after that, we have characterization. And what is the characterization? The characterization is the calculation of the indicator results for each category, and it's done using characterization factors and models. And this is a quantitative process, of course. And here, a very simple example. We have in a determined system, we have emissions of 1,200 kilograms of carbon dioxide, 20 kilograms of methane, and 0.1 kilograms of nitrous oxide. Of course, according to the IPCC method, the global warming potential, the characterization factors for the carbon dioxide, it's 1, of course, because we are measuring the impact. We are measuring the indicator we are calculating the indicator in kilograms of like carbon dioxide equivalent, and then as we are emitting carbon dioxide, the characterization factor is 1. And then we have the characterization factor for the methane is 28, which is equivalent to say that each kilogram of emitted methane is equivalent to 28 kilograms of carbon dioxide. So we need to multiply the 20 kilograms for the characterization factor of 28. And then we have the emission of 0.1 kilograms of nitrous oxide, which has a characterization factor of 265, which means that each kilogram of nitrous oxide it's equivalent to emit 265 kilograms of carbon dioxide. So we have to multiply, and then we sum the values, and we obtain the indicator for the impact category climate change. This is a very simple example, of course, and it's done for each one of the analyzed impact categories. So, and then for the example of the shirts, the 1,000 shirts, the results of the life cycle impact assessment. Of course, that study has some scenarios, but to simplify, I haven't spoke about it. But we can see in S1 the results for each of the impact categories assessed, which were abiotic depletion, acidification, eutrophication, global warming, and human toxicity. And for each one of the stages of the life of the considered stages of the life cycle. And as you can see, for the global warming is more or less it's more or less similar between the cotton production, the yarn production, and the fabric production. But for example, for the eutrophication, the cotton production is much more intensive than the other stages due to the use of fertilizers in the cotton production. Then we have the phases of life cycle impact assessment, which are not mandatory, which are optional, and one of them is the normalization. And what it means to normalize the results of the life cycle impact assessment. It means to relate those results to a reference value, and that reference value could be the value. For example, we obtain for our product, we obtain a certain amount for the global warming potential, some 10 kilograms of carbon dioxide equivalent. So to normalize that value, we can divide it by a reference value that usually is a reference value for a geographic location, or for Europe, or for world, and we can divide our result by that reference value, and doing that we can know which of the analyzed impact categories as more importance in our product system, because we are referring it to a certain reference value, and of course it's a dimensionalized value, so we can understand which of those impact assessments it's more important in our product system. And we have the normalization factors. We have some normalization factors for some of the methods. For example, here we have the normalization factors applicable to CML 2001 method for the different assessed impact categories. And of course, these are the equivalence is the reference value. And that means, for example, for the global warming potential, that the emissions of carbon dioxide equivalent in the world have that number. So we divide the number obtained in our system product by that, and we have an dimensionalized value, and we do that for all these impact categories, and we can understand which of them has more importance in our system product. For example, here we can see the normalization of a certain product, and for three different impact categories, and the results of the life cycle assessment were normalized for person per year, and then we can understand, we can see that in that specific system product, the category with more representative is a particulate matter and not acidification or the climate change. So, and this is what we can obtain from normalization. Then we have the weighting. The weighting is nothing more than to get the results for the different impact categories and attribute different weights to each of them to calculate one single environmental impact indicator. Of course, this is not easy. It's not easy because there are not. It's difficult to find some reference values to do this weight, and this is up. It's more or less up to each of the author studies, and depending on the objectives of the study, to attribute more weight to a certain category than other category. And the goal of the weighting is really to have one single environmental indicator, some weighted results, and this is very useful, for example, to compare two different products, because, like I said before, taking into account the same example, the polyester fibers and cotton fibers, we can have different interpretations if we are looking to different impact categories. So some product can have more impact in some category, and the other product more impact in the other. So, and the weighting, it's something that is important, and that could be important, and it would be useful to have some reference values to do it. But of course, we were talking about the way that the impact assessments and also the life cycle assessment studies, mainly the inventory, the life cycle inventory and the life cycle impact assessment are made. And of course, nobody do that without help of a software tool specific for LCA analysis. And those here presented are the most used life cycle assessment tools. Sphere LCA, the former, I don't know if you heard about Sphere LCA, but if we say Gabi, maybe more of you already heard about Gabi, which is a very used software for LCA analysis, as well as CIMAPRO and Umberto. And of course, I put here some. We use here in CITEV the Sphere LCA, the former Gabi, and this is the aspect of the homepage of Gabi. And then here we have a system product representing the dye of the dyeing of a polyester fabric, dyeing and printing of a polyester fabric. This is the system products, but for example, when we click in the rotary screening printing, we open. This looks simple, but then we open the one of the stages, and it models a lot of situations, the core process, but also it is included that the natural gas used to produce the steam needed for the washing. Here is the washing of after the printing with disperse dyes, and it uses steam. That steam is produced from natural gas. It also used water. It used some chemicals. Those chemicals have to be bought somewhere and had transport associated. That transport had a consumption of diesel, and those of this. And after the washing, the wastewater is sent to a wastewater plant, and it is also we also consume electricity in that process, and also in the wastewater treatment plant. So all of these aspects are included in the model, and it is what we do in life cycle assessment, is to build the model of the life cycle for each unit processes, like we are saying. This is the different unit process. For each unit process, we build a model with, and then in that processes, we have the inputs, and we have the outputs. And this is the model that is built usually in the software tool, and then we apply the methods for impact assessment and for the different impact categories, and obtain the results. Then we pass to the last phase of the LCA analysis, which is the interpretation. And the interpretation, it means it's a step where we look for our results, and we compare it with our objectives defined in the golden scope the definition. Of course, the interpretation of we can identify. The interpretation is to look on the results and compare it with our objectives, and find, of course, the conclusions and the limitations of the study, and the recommendations of the study. Of course, in interpretation, we interpret the results, not only the results for the impact assessment, but also the results of the inventory, of the life cycle inventory. And we evaluate those results, and we have to evaluate those results, and that evaluation must comprise the following items, which is the integrity control, to ensure that all of the relevant information is available, sensitivity and uncertainty analysis, consistency control, and also and after that the conclusions and the limitations of the study. And here, and a very simple example of an interpretation the example that we are accompanying to the webinar. The objective, if you remember, the objective of this study was also to understand, one of the objectives of this study was to understand what were the hot points, the phases of the life cycle of that product, which have higher environmental impact. And of course, here analyzing that graph, analyzing that figure, we can see that, of course, the fabric production on most of the analyzed environmental potential categories, each is one of the odd points, as well as the cotton production. Mainly in the acidification potential and the eutrophication potential. The production of the cotton is also an odd point for those two categories. And this is a very simple example, but it's how interpretation. It's one thing that we do in the interpretation phase. Then let's speak a little bit, and I'm accelerating a little bit now, and this last phase, because we are almost on time for the 10 minutes that I left for questions. So if we want to communicate the LCA results, we have some additional requirements for if we want to communicate with comparative assertions to be discussed to the public. And those requirements are related with the data quality. It demands more primary data. Sensitivity analysis is mandatory in this case, also to check if we make some assumption, some important assumption, we have to perform sensitivity analysis to test those assumptions. Also, very important is the critical review by a review panel of at least three specialists, and we have to analyze more than one life cycle impact assessment indicator. And also there are some other requirements for reporting of these LCA studies. But on this slide was important to launch the previews, the next theme and the last one of this webinar, which is some communication tools to communicate the environmental impact of our products, which are two main tools that we will speak a little bit about, which are environmental product declarations, EPDs, and environmental and the product environmental footprint, which is PEF. So this table is a resume table of these three methodologies: the life cycle assessment, the environmental product declarations, and product environmental footprint. The life cycle assessment, as we saw, the methodology is based on the framework of the ISO 14040 and 14044, and the impact categories are not defined. It depends on the goal and the scope of the study. When we are speaking about environmental product declarations, the environmental product declarations are based in a LCA study. That LCA study must comply with the LCA standards, 14040 and 14044. Additionally, that study has also to comply with ISO 14025 and to the specific product category rule applicable to the product that we are analyzing. Of course, and the impact categories assessed are dependent on the product category rule. And then we have the product environmental footprint, which is also based on a LCA study that shall be performed according to LCA standards and also according to the EU recommendation 2021-2279. and the product category rule, which in the case is named not PCR but PEF-CR, and it always analyzes 16 impact categories defined in the methodology. So, and what is an EPD? An EPD is a declaration that presents quantified environmental information of the life cycle of a product in order to allow comparisons between products that perform the same function. And of course, it shall be products that perform the same function. It is based on LCA study results, made also according to product category rules for that specific product, and has to be that study has to be verified by an independent third party, and it's not that verification is not a critical review. It's a little bit different. The verification is to check if the study was made according all the standards and the product category rules applicable to that product. And it depends also and it has also registration in a platform and a specific platform for that. And for example, for textiles, we have the platform, which is the EPD, the international EPD system, that have some product category rules for textile products, where textile companies can register those environmental product declarations. And the methodology is simple: select the applicable product category rule, to perform the LCA study according to the product category rule and the remaining applicable standards. Put the LCA results in the EPD model that is always available in the platform. Request a third-party verification, and then after the EPD is verified and the LCA study, to register the EPD in the platform for its publication, for its availability to the public. Here is an environmental product declaration of a product that is in the EPD system for a textile product, which is a yarn made by this company. And we can see in the figure of the right the parameters, the impact categories, the impact category indicators that have to be calculated for this EPD for this product. They are calculating those category rules because there are the mandatory category rules stated in the PCR of this product. Then we have also a good way now to communicate, which is a product environmental footprint. And the environmental footprint methods were an initiative of the European Union to create two methods, one for products, the other for organizations, which is the OEF, Organization Environmental Footprint, and to provide some harmonized rules for conducting transparent assessments of the environmental impacts of products, and also of the organizations, using the life cycle assessment methodology. As you see, the framework of the PEF is very similar with the framework of a normal LCA study, with the 4 phases: the goal and scope, inventory, impact assessment, and interpretation. But here it has another part, which is the verification, also the verification of the study. In order to conduct the LCA studies for a product environmental footprint, there are also some product. There are also product category rules. There is stated that it's finished a product category rule for t-shirts, but this PEFCR, which is the meaning of product environmental footprint category rule for t-shirts, but that's the product category rule was made in the pilot phase and is no longer valid and is no longer valid. So right now they are developing product category rules for the apparel and shoes, for apparel and shoes, like we can see in the following slide. They are developing PFCRs for t-shirts, shirts and blouses, sweaters, jackets, pants, dresses, and this kind of apparel and shoes products. And that's a good methodology because it has some harmonized approach, which demands that everyone that conducts a life cycle assessment study according to PEF must follow that recommendations, that product category rules, and in that case we can have comparable results and results that were obtained for an harmonized methodology, and not because what mostly happens nowadays is that each one that performs a life cycle assessment study performs according to their own assumptions. They assess the environmental impact categories that they choose. They use the data, the quality of the data that they choose, and in that case, we have harmonized standards that it's a recipe that we have to follow to obtain the results, and in that way, the results are comparable with other similar products made with the same methodology. And the last slides here are the impact categories that we have to analyze during if we conduct a product environmental footprint analysis. But as I said before, the product category rules for the apparel are still ongoing, and they are not available. But we hope during this year, or at least in the beginning of the next year, we believe that they were available for public. So, and with this slide, I finish what I have prepared. I'm sorry because I'm a little bit late. I was planning to end at 11:45 to have time for questions, but now I open the debate to some questions that we have right now.
So I already allowed the microphones and the cameras, so please, I encourage you to step front into the questions, or some doubts, or some maybe inputs that you can provide to this conversation. Okay, we have
Good
David.
morning, everybody. Yeah, my name is David Crapanzano from Propa Group Italy. Yeah, a very basic question, please, if you can clarify something about the data quality. if there is any public body to assess the quality of the data that are provided within an LCA analysis. Thank you.
So no, as far as I know, there isn't any public authority who assess the quality of the data. The quality of the data, as I said before, it depends mainly on the goal and scope of the study, and also if we are performing the study with reference to a product category rule for an EPD, or a product category rule for the product environmental footprint. The quality of the data must obey to what is said in the product category rule. For example, usually in the product category rules for the EPDs, it's mandatory, and I think also for the PEF, in the methodology defined for the PEF, is mandatory for the core production process. It's mandatory to use primary data. It's not possible to use secondary data. For example, if we are making a T-shirt, you cannot use secondary data to model the dyeing of the T-shirt, or the spinning of the yarn that are used in the T-shirt. It's not possible to do that. We have to use primary data. And of course, when we are performing an LCA study, and if we have a critical review, of course, the review panel or the review specialist will look at the data and check if the data complies with says in the standards or in the product category rules, and they will validate, or they will put something in the report to classifying the quality of the data that we were using. But public organisms that are assessing the quality of the data, no. But of course, if we are the best way to have it validated is to perform an LCA study and to ask for a critical review, or we create an environmental product declaration or a product environmental footprint, which is verified by an independent third party. And of course, that validation, I think, is enough to ensure the quality of the data.
Great, thank you. Very clear.
And anyway, if you don't have questions right now, but if you want to make any questions further, you have my email in the presentation, and you can also contact me later to clarify some subject. There is no problem.
Email for
Sorry,
contact.
I'm not listening. I'm not hearing. Raquel?
Yes.
It was you speaking, because I'm listening with some cuts. I didn't understand.
Right now?
Okay, better, much better.
Okay. So we will provide all the materials and Luis' email for further contact. And thank you for everyone to listen to us today. And I hope to see you again in the other training activities. Thank you, Luis.
Thank you very much also from my side. And have a good day.
Goodbye.
Bye.
Thank you. See you all. Bye-bye.
Bye-bye.